Okay, let's get started. So lab 3 is due, lab 4 will be out today. So today we are going to talk about large language model efficient deployment techniques. And one of the algorithms we learn in our AWQ will be part of the homework. So I will also be helping you to deploy a large language model on a laptop for lab 5. So today's lecture will be super interesting. So let's get started with LLM deployment techniques. So here are the 3 major chapters we are going to talk about today, starting with quantization, with 8-bit weight activation quantization, and then weight-only quantization, and then we combine the best of both worlds to talk about QServe, quantizing both weight and activation to low precision. Then we are going to talk about applying sparsity to large language models, weight sparsity, contextual sparsity, attention sparsity, and finally system support for large language model inference. So inference these days is getting super important. If you see GPT 4.01, the inference time scaling is getting super crucial. So increasing the inference efficiency is a very important topic for efficient LLM. So here we'll talk about metrics for LLM serving. I'm using paged attention, flash attention, speculative decoding, and also use-fly batching techniques. Okay, that's the agenda. Let's start with the first part, which is quantization. Today's lecture is pretty dense, so let's move on quickly. So a brief overview of quantization. We briefly chatted about quantization in lecture 5 and also lecture 6. So we can cast a floating point number into an integer from using 16-bit to using only 4-bit. So lots of the quantization techniques, including what we learned in lecture 4 and lecture 5, does not quite apply to large language models. So if we see when the model size gets pretty large, from 1.3 billion to 6.7 billion, 13 billion, 175 billion, the accuracy for the 8-bit quantization is going to drop. Okay, so it only works for those small models. But when the model gets much bigger, those algorithms that traditionally work for CNNs does not work for large language models. And what is the reason why we cannot apply previous quantization techniques to large language models? Actually, the reason is due to these outliers. Okay, the activations in certain channels is pretty big, super big values. They are going to destroy the accuracy after quantization. So we visualized the activation value across different channels. So here we have 5,000 channels, and this is across different tokens. Here we have 300 tokens. We can see 3 outlier channels. Okay, so across different tokens, their activation value is consistently pretty large across different tokens. And you can see the value on the y-axis, they are pretty big, much bigger than the remaining activations. So what happens if we quantize this tensor? So all the values in the blue area will be clamped to 0. Since these outlier channels are wasting the dynamic range, right? So all these blue values will be clamped to 0. So that's the new problem. That's the quantization difficulty for large language model. Okay, but the weight, okay, the weight is actually pretty flat. You can see it's all blue, right? So the weight is very easy to quantize, and the activation is super hard to quantize. So how do we deal with that? How do we mingle the weights and activations and balance the quantization difficulty? Can we migrate the difficulty? Actually, yes, because the matrix multiplication is linear. We can multiply this channel by 0.1, multiply the corresponding weight channel by 10. What happens? So 0.1 times the 10 equal to 1 by 1, right? It's linear, so we can scale them and push the quantization difficulty between weight and activation. And the result will be still mathematically equal. So here we migrate the quantization difficulty by shrinking the activation and increasing the weight, so now the activation becomes easier to quantize and the weight becomes harder but still relatively easy to quantize. You see some of the channels are getting larger due to we are multiplying the weight with a larger number, multiplying the activation with a smaller number. Just like 1 times 100 equal to 10 by 10. You can use that to equalize between, to smooth between the weight and activations. And we are effectively migrating this quantization difficulty from the activation to the weight. And the result is mathematically equal. So let's see an example to digest this algorithm. So this is before, this is after. So before SmoothQuant, this is the original activation, this is the original weight W, activation X. X will be multiplied with W. The input has two sequences, okay? 2 sequences. Each one has 4. Each one has 4 hidden dimensions, okay? And here the W also has 4 input dimension and 3 output dimension. Okay, so this column will be multiplied with this column initially. Unfortunately, initially we have these 2 outlier channels, 16 and 8, 6 and 9 in the activations. We colored them. The red color corresponds to the bigger value. Okay, so the white color corresponding to smaller value. But you can see the weight, the color is pretty white. There is no outlier here. So how do we migrate the quantization difficulty from activation to weight? So let's first see the result. Okay, so this is after SmoothQuant. These 2 outlier channels, 16 and 8, now become 4 and 2. 6 and 9 becomes 2 and 3. So previously 16 will be multiplied with 1. Now 4 will be multiplied with 4. So 16 times 1 equal to 4 times 4. So the result is the same. Similarly, previously 8 times 1 now is 2 times 4. It's still the same. Okay? So after we can see after this transformation, the result of the weight multiplied by activation doesn't change. So how did we achieve that? And let's see the derivation. So let's first find the absolute value, the max of the absolute value of each column. In the first column, the absolute value max is 2. Second column, the max of the absolute value is 16. Third column, the max of that absolute value is 2. Fourth column is 9. Right? So we get a max of the absolute value of activations. For the weights, we do it in another direction. For the first row, we get the max absolute value 2. Second row, third row, and the fourth row. Okay? So we get 2 vectors. One is the max of X, absolute value. The other is the max of the absolute value of W. And we put them here. So this is max X, this is max W. What we do is we divide X by W, okay, and find the square root of that. Like 16 divided by 1 square root, we get 4. 9 divided by 1 square root, we get 3. So we get a scaling factor of 1, 4, 1, 3 in this case. So this is during the calibration stage. We run a few batch of sentences, and we collect these statistics, collect this activation information, and we collect the scaling factors. We do the division between the weight and activation and square root of that. We find this scaling factor. So the next step, we apply the scaling factor. So by dividing X with the scaling factor, and then multiplying W with the scaling factor. Okay? Same scaling factor, one is divided by that, one is multiplying with that. So mathematically, it's the same. Okay? So it's X divided by S, and W multiplied with S. And these S will cancel each other. Okay? So let's see what do we get. So X divided by S, element-wise, we get this output. Okay? Scaled the output channel by x. So now it's smoother than before, right? Previously we have 16, which is a big outlier. Now it becomes 4, which is much smoother. And W will row-wise multiply with this scaling factor. So it becomes this matrix. And in the end, we have the transformed x, okay, and the transformed W. So after such transformation, the weight matrix, activation matrix are becoming both easier to quantize. So let's see, this is the final result. At inference time, there's no scaling. Okay? Scaling can be folded into the previous layer at compile time. Okay? So at inference time, we are just calculating the multiplication of these two matrices, the scaled x and the scaled w. And they're all in integer without any runtime overhead. And the outlier problem is also solved in this case. Since we are pushing the quantization difficulty from activation to the weight, there is a strength. How much do we push, right? Do we push all the difficulty to weight? That becomes this extreme. We push nothing to the weight. This is the other extreme, pushing everything, all the quantization difficulty to the activation. Here we are pushing all the quantization difficulty to the weight. Actually, if you compare the accuracy, none of them is good. But in the middle, that's the sweet spot, okay? Roughly 0.5. And that's why we did the square root right here. Okay, we find the square root right here. That's corresponding to the general case where we are having the x to the power of alpha and w to the power of 1 minus alpha. Alpha is the migration strength, determining how much quantization difficulty do we push from activation to the weight. The larger the alpha, the more we are pushing the quantization difficulty to the weight. And weight becomes much harder to quantize, activation becomes easy. The middle is the sweet spot where the accuracy maintains pretty high. So practically 0.5 or finding the square root is a very good recipe. Okay, so we integrated SmoothQuant into faster transformer. So this is the precision flow, the precision of each compute node. The yellow one is at P16, the green one is int8. We want to have all the compute intensive operations, like linear operations, batch the multiplication, to be done in the quantized manner. So these green parts are all in quantized manner, like QKV, BMM, another BMM for the attention, output projection, FFN1, FFN2. They're all performed in int8 versus this nonlinear layer like layer norm, softmax, layer norm, element was add. They are done in FP16 to preserve the accuracy. And here the bypass branch and the second bypass branch and the input to the layer norm, they are done in linear. They are done in the P16 manner to preserve the accuracy, and they are not compute intensive. So it's fine. It's fine to keep them in P16, occupying very little latency. So this is the system implementation part. Combining the system implementation with the SmoothQuant algorithm, we can well preserve the accuracy across different models, big models. This is P16, this is the SmoothQuant version, maintaining the accuracy while reducing the serving cost. Previously, it required 8 GPUs to serve this 175 billion parameter model. Now it requires only 4 GPUs to serve this 175 billion parameter model. Okay? And if you see the latency, we reduce the GPU by half. The latency even shorter. It's even shorter, right? Even faster because of the reduced communication overhead. And the memory is also reduced by half, having fewer GPUs. Each GPU is pretty expensive, so it makes a lot of sense to reduce from 8 GPUs to 4 GPUs and have the same quality. We even scaled it up to a 530 billion parameter model. Okay, we want to serve that in a single GPU node. Why it's good to serve the model in a single node rather than in a distributed manner? Communication overhead, right? We want to fit the model in the node so we don't have to communicate, easier to parallelize, right? Previously, if the sequence length is about 12, you require 16 GPUs to serve this Megatron Turing NLG 530 billion parameter model. Okay? That requires 2 nodes. Each node has 8 GPUs, 16 GPUs, that's 2 boxes, okay? And after applying SmoothQuant, we apply int8 quantization, only 8 GPU can fit, and the latency didn't change much. Pretty much the same, in having the GPU memory and having the number of GPUs right here. Okay, so SmoothQuant also works for newer models like Llama, and this is comparing the P16 versus SmoothQuant across different benchmarks, turning a larger Llama into a smaller Llama. Okay. All right, so that's the first algorithm of LLM quantization, SmoothQuant. So we want to continue to push forward to use fewer bits, right? So I'm going to introduce the activation aware weight only quantization that push the weight precision to only 4-bit, from 8-bit to 4-bit. And also the TinyChat, which is a system that supports to implement the AWQ algorithm. So here we want to target on-device, single batch, single user inference. So on-device LLM inference is pretty helpful where you want to interact with your device locally without communicating your data to the external, to the internet. So the weight is actually the bottleneck. So from larger batch to a smaller batch, the compute intensity is much lower since matrix multiplication becomes matrix vector multiplication. You still fetch the same amount of weight, but a lot less reuse in matrix vector multiplication. So we want to alleviate this bottleneck caused by the weight memory access. So here the x-axis is the compute intensity, fetch 1 byte of data, how much flops you can do. The y-axis is the t-flops, teraflops per second. So we need low bit weight only quantization for this setting because the activation is not the bottleneck here. Weight is the bottleneck in the single batch serving. That's why we quantize the weight to extreme and leave the activation in 16-bit, and also leave the arithmetic in 16-bit, since for low batch arithmetic is not the bottleneck, but weight is the bottleneck. And here we are focusing on the generation stage, okay, which is the red part. So compared with the black part, which is the context stage, the context here has 200 tokens, and the generation, you want to generate 20 tokens. The generation stage is the bottleneck, occupying the majority of the total inference time. And second figure is showing that we are focusing on the generation stage, but the generation stage is bounded by the memory bandwidth. Okay? So the red curve here is the P16 version. The yellow curve is the int8 version, and the green one is the new one we are proposing here, int4 for the weight, P16 for the activations. In the switch region, when the batch size is small, when the computation intensity is small, the W4 version has much higher achieved performance. And on the right-hand side, we are comparing the weight versus the activation. The weight is in red, activation is in black. So weight, this is the logarithmic y-axis. And you can see the memory footprint for the weight is like 70 times more than the activation. And here for the FFN, it's over 1,000 times larger than the activation. So weight is the focus. We want to do weight only quantization in this work. So given that setting, let's see, what if we do them naively using what we have learned in the lecture so far? So this is the weight matrix. It is 8 by 4. Initially it is FP16. We want to quantize it. Given the space limitation, we quantize it to int3, 8 choices. Unfortunately, naively doing such round to nearest quantization, there is a big, very strong degradation for the perplexity measured on Wikitext2 dataset. A very strong degradation on the perplexity, a big change, a big increase, big degradation for the perplexity, which is too bad. Showing that our conventional algorithms will not work. So what do? Interestingly, we find just preserving one row, in this case 1%, okay, 1% of the salient weight channels unquantized can greatly improve the perplexity. Okay? Just have 1% of the channels, keep them unquantized, we can save the perplexity. And you can see immediately saving the perplexity, reducing the perplexity when having 1% of the models unquantized. But the interesting thing is, how do we select those 1% of salient channels? When we are quantizing the weight, it's very natural to look at the weight distribution, the weight value. For example, when we are pruning the weight, we prune away those small weights. When we are quantizing the weight, naive solution is to look at the weight. For example, if the weight magnitude is large, we don't quantize it, right? But counterintuitively, AWQ find that we should not look at the weight when quantizing the weight. We should look at the activation when we are quantizing the weight. This makes sense because the weight will be multiplied with the activation. And we have this outlier problem in the activation. Some channels, like this red channel, may be super big, to others of magnitude larger. So if you are changing the activation, if you are changing the weight by a small disturbance, by a small amount, it will disturb the final value a lot if the activation is large. Because this activation, the second column here, will be multiplied with the second row. Okay? So this row will be multiplied with a pretty big number, then we should protect this row. So that's where the AWQ comes from, activation awareness. Question?
Yeah, what's perplexity?
Oh, perplexity is the measurement of the quality of your language model. So it's basically showing, comparing your output versus the ground truth output. The lower, the better. Okay, so this is showing activation has a lot of outliers. We should look at the activation, but not the weight. So this is comparing, look at the weight, look at random selection selected by weight versus selected by the activation. And there's a big improvement for the perplexity by selecting based on the activation, not the weight. But the problem, there is a real problem here, right? Here we are keeping 1% of the channels unquantized. They are in FP16. That's very difficult to implement if you have both int4 and FP16 in the same tensor, which will introduce mixed precision, which we don't like. That makes the inference library very complicated. So is it really necessary to introduce mixed precision? Is there a more efficient way to get rid of this 1% of floating point number? Actually, there is a way to do that. Okay? So we can protect the salient weight by simply scaling them without mixed precision. Okay? By simply scaling them. This is inheriting the intuition of SmoothQuant. Okay? If we multiply, scale the weight, and scale the activation in a reverse manner, they can cancel each other. Okay? And also the result will be the same. Here's some notation where the quantized weight equal to, we first calculate this delta, which is the quantization scalar, which is the IBS max within the group. Okay, so the delta is the range, the max value, and then we round the result, dividing W by this max value to the power divided by 2 to the power of n minus 1. N is the number of bits. Okay? So we can actually scale the activation to protect it. That's actually super effective. If we multiply the setting channel by 1.5, the perplexity reduced from 43 to 14. Multiply the setting channel by 2, reduced to 14. Multiply by 4, 14.4. Okay? So this is a very interesting observation. You don't need to keep it in IP60. You only need to scale up if a channel is sedate. Then how do we decide how much do we scale? You can see here, if you scale at the right amount, like 2x, it's very big saving, but if you scale it by too much, like 4x, the perplexity will get worse. So intuitively, if you are scaling only one channel by 2, other channel remains the same, you are effectively adding 1 more bit. If you scale it by 4, you are effectively adding 2 more bits, right? Say, give an example, 0.5 and 1. Without any scaling, 0.5 will be rounded to 1. You cannot distinguish them. But if you scale them, 0.5 becomes 1. 1 becomes 2, right? And so you can distinguish them now, assuming other values stay the same. Okay, so that's the simple intuition behind why scaling up a channel will protect it. Okay? Previously, something cannot be distinguished. Now you can distinguish them. Okay, so let's dive deeper mathematically why scaling it up will work. So on the left-hand side is showing this is the quantized weight multiplied by the activation. So this is the quantization equation we introduced in lecture 5. And this is a scaled version on the bottom, scaled version of W, scaled version of X. We just plug in as to both the weight and activation. And now we want to calculate the error. Okay, the error of the quantized weight times the activation. We just plug in the equation here on the left. Delta, the quantization scalar, is ABS max within the group, so it has no error. But this rounding function, all the error comes from this rounding function. Okay? So the rounding function ranges from 0 to 0.5, right? So the expectation is 0.25 if you have a lot of numbers. So this rounding function's error, the error of this rounding function has an expectation of 0.25. And if you have the scaling factor s here, s is multiplied with x. X is divided by s. And since we are scaling them up, s is greater than 1. So plug in this equation, this ABS max within the group stay roughly the same, since you're only scaling up 1% of the channel. It's very unlikely you are scaling up the biggest channel. So this delta roughly stays the same, and only this s is different. So that a larger s will reduce the error. So can s get infinitely large? It cannot. Otherwise, it will impact this ABS max, this delta. Okay. So s cannot get super big. As we can see, when s gets bigger from 2 to 4, the perplexity will get larger, will get worse, because they are destroying those non-salient channels. So next question is, we need to search for the best scale. How do we how do we scale the activation? So here is a recipe. Okay, so the scaling factor is the average activation magnitude as x. X is the activation, as x is the average activation magnitude to the power of alpha. Okay? Alpha is the hyperparameter we can search from 0 to 1. And we want to minimize this scaled WS versus the original WX. And here the S to the power of -1 can be fused to the previous operation. Remember, we have the pre-norm. So the normalization comes before the matrix multiplication. And the layer norm has a scaling factor. And this s to the power of -1, this scaling factor can be effectively folded into that operation. And when we are scaling the weight, it's also static because we know the weight ahead of time. So weight times scaling factor can be calculated offline. So there's no runtime overhead in this case. Okay, so that's the algorithm of AWQ, and let's see how that works. So this is the perplexity, the lower the better, between GPTQ and AWQ. So this is a calibration sequence. Actually, we require very little, very short sequence, like 64 sequence. Then the perplexity is already pretty low. When we have a very short calibration set, the perplexities are also much lower than the baseline. So this method doesn't require any back propagation. So it only requires a calibration data set. It doesn't require this regression-based method, which tend to overfit and doesn't generalize. Okay. Also have very good data efficiency. Only very short calibration sequence can help a lot and generalize quite better to across different data sets. For example, PubMed, which is a medical data set, INRAN is a corporate email data set, two completely different domains. Using the baseline method, the GPTQ method, the perplexity increase a lot, like 2 or 4 points when you are switching between a different calibration data set, different calibration data sets when you are using the actual data set on test, under test, versus AWQ can have very minimal perplexity increase when you are switching the calibration data set. That is different from your accuracy testing data set. And this is showing AWQ for large language model quantization for Llama, Llama 2, of comparing different approaches across different model sizes from 7B to 70B. The accuracy, the perplexity is pretty low. AWQ also works for visual language model. Okay, so basically, given image or video, you want to tell what is happening and do question answering. We're going to talk about that in the later lecture. Like given a video, here is a football soccer game. Please tell me what happens in the video. And this is run live at villa.mit.edu. Feel free to check it out. This is deployed using the AWQ algorithm, deployed on a single GPU. The question is, please tell me what happens in the video. Villa says, a video shows a soccer game where a player scores a goal, the crowd cheers, and the player celebrates with his teammates. And this is using the AWQ 4-bit version. So here we compare the P16 version versus the 4-bit version. The accuracy across different benchmarks is pretty well maintained for both the 7B and the 13B model. And to implement, there's a question?
Was that the one, was that the one that called the 12 lab?
Which lab?
It's called 12 labs, and understanding the video from.
I'm not aware, I don't know.
Okay.
There are many users of Villa, maybe that's one of them. We don't know.
That's their advertisement to have it running on a single GPU to do just like that.
I'm not aware. We did this, I think, this work was in June 2024, and all the demo is available earlier this year, actually. Okay, so how do we implement the 4-bit AWQ model? Okay, so we have an engine, developer engine called TinyChat, our inference engine on the edge device. So TinyChat is a lightweight large language model inference engine that is based on Python. We have a lot of low-level implementations, but we expose to the user the Python interface, very lightweighted, efficient, support multiple platforms, CPUs, GPUs, etc. So we want to target two figure of merits, make it efficient, and also make sure it's easy to use. And support multiple platforms, including the cloud, desktop, laptops, which you will implement that in your homework, Lab 5, and also edge GPUs, mobile CPUs, etc. A problem here is that since since 1960s, computers has been byte or byte. The minimum unit of computer is a byte, and a byte is 8-bit, right? While AWQ quantized the weight to only 4-bit. So how do we align this mismatch? Every register, okay, this is the weight register. Okay, each register have to store 8-bit, but each weight is only 4-bit, which means for each byte we are going to store 2 weights. And we want to decode the weight such that we can exploit the register level parallelism. So this is the original weight. Okay, this is the weight we want to process. So for every 2 boxes that indicate a byte, 4-bit in each rectangle represent 4-bit. Okay, so the motivation here is to be able to we want to easily decode the packed weight. Okay, so here we want to store the weight in this manner rather than storing consecutive manner like 31st, 30, and then 15, 1, 0. Okay, we want to store them in this manner. 31 first, and then 15, and then W2, 17, 1, 16, 0. Okay, in an interleaved manner. So if you just look at the gray part, they are consecutive 0, 1, 2, all the way to 15. If you look at the red part, they are consecutive, like 16, 17, all the way to 31. Okay. So we can perform 2 low-level operations to decode it. First, we can mask this vector with the lowest bit to be 1, okay, the highest bit to be 0. Then we can decode the lower bit. The mask would be 0f, 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 0f. And then we can shift by 4, shift these packed weights by 4-bit, and then mask it. After shifted, the red part go to the bottom. Okay, and after masking it with the 0f, 0f, we get the top from W31 to W16. Okay, and using this packed approach, we can reduce the latency, okay, about 20% speed up our ARM Neo. Another important technique is kernel fusion. So in the parallel processing lecture, we talk about the overhead of kernel calls in the GPU, so it's not free lunch. Launching each kernel is taking a lot more time than you expected. So we want to fuse all these operations in a single kernel. So BNM, QK transpose, softmax, and then multiply the attention map with the V, the value vector. And all these we want to fuse them into a single kernel for the attention. And also we want to fuse the kernel for the jam. Okay? In the context stage, we also want to have a single kernel for the jam. After these techniques, TinyChat can significantly be applied to accelerate the edge language model. So this is deployed on a desktop GPU, a laptop GPU, a mobile GPU. This is Jensen Orion widely used in self-driving cars. These baseline, those are the gray part is at P16 speed. The red part is the int4 AWQ result. On these 3 different benchmarks and different hardware platforms, AWQ can achieve roughly 3x speed up. And previously, some of the models cannot fit the laptop GPU due to the GPU has only 8 GB of GPU memory here, the laptop. So FP16 completely runs out of memory, but the AWQ version can fit. So this is comparing AWQ with other frameworks like AutoGPTQ, Llama.cpp, EX-Llama, etc. on a Jetson Orin mobile GPU. We built a TinyChat computer, which is right here, which is powered by Jetson Orin Nano. And we can run Llama 2.7b on this TinyChat computer. It's 3D printed. And inside, in the back, it has a Jetson Orin Nano, which is right here. The board has about 7 gigabytes of available memory, and TinyChat can quantize the Llama 2.7b to 4-bit, so that requires 3.5 gigabytes of weight memory. It can fit well in a 7 gigabyte device. You can also scroll to see the previous outputs. So such mobile development can enable data privacy and security. Even without the internet, enable customization and personalization. And after lab 5, you will going to see, bring your home, something like this. Deploy a large language model on a laptop, either a CPU laptop or GPU laptop or a MacBook. So on the left-hand side is showing only 25 milliseconds per token, while on the right-hand side, we are trying to write some code to compare two arrays on a MacBook. And this will be exactly the same thing we are going to do in lab 5. So in lab 4, we are going to first do AWQ quantization. In lab 5, we are going to implement the quantized model on your laptop. So make sure your laptop has more than 8 gigabytes of memory. Okay, so this is showing the speed up on cloud GPUs, desktop GPU, gaming GPU, and also the mobile GPU. Okay, so A100, 4090, and Orin. Tokens per second means how many tokens it can output per second, it can generate. So comparing the baseline version, the Intel 4 AWQ model consistently deliver about 3x speed up over IP16 on the Orin platform. So this is the Orin platform, which is a mobile GPU. We are running Vila, visual language model on it. What is unusual in this image, and it's going to say there is a herd of deer crossing the street. A car is waiting for them to pass. What should the driver keep going? No, the driver should not keep going. Should wait for the deer to cross the road, etc. Okay, running at about 43 milliseconds per token. Also, this is a visual language model demo runnable on a laptop. So what is the name of this painting? This is with the M1 chip running on the CPU, not even the GPU. And it's going to say portrait of Mona Lisa. And who drew this? Leonardo da Vinci. And describe the painting in detail. And it's going to talk about that. Running it live without transmitting your pictures, languages to the cloud. So in our homework 5, lab 5, we are just going to implement the language model without the image, but feel free to also support image in lab 5, which could be part of your final project, which is open-ended. So AWQ also has a lot of downloads, a lot of uses. At the time when we make the slides, it's 1 million downloads, but now it's already over 6 million downloads on Hugging Face, being used by NVIDIA TensorRT LLM, which is a flagship library for large language model deployment and inference, IBM, Berkeley, Chat, Transformer, Hugging Face Transformer, etc. All right, let's take a break before we jump into the next part. All right, welcome back. We spent a lot of time talking about SmoothQuant and AWQ since they are going to be in lab 4, so we talked them in very detail to strengthen your understanding. Now let's move on to combine the best of both worlds between SmoothQuant and AWQ. So let's first look at the difference between AWQ and SmoothQuant. So here, the red curve is showing the SmoothQuant, where we are having 8-bit for the activations. So the red curve here is showing IP16 LLM, while this orange curve is showing the int8 LLM. Right? So the SmoothQuant is basically int8 for both the weight activation and also the KV cache. We notate it by W8, A8, KV8, KV for KV cache, A for activation, W for weight. Okay, so this is pretty good for the cloud serving W4, A16, KV16, which is the AWQ setting, 4-bit weight, 16-bit activation, 16-bit KV cache. That's good for the edge inference. Because for the cloud serving, usually they are having a pretty big batch size. Okay, the popular setting is W8, A8, where the weight is 8-bit activation, 8-bit, and KV cache is using 8-bit per tensor quantization. It can improve, it can lift the roof line. Okay, so previously it's 1 trillion numbers per second, since each element is 2 bytes. In FP16, in int8, each element, each number is only 1 byte, so we can process 2 trillion numbers, calculate 2 trillion numbers per second. Okay? Also have a bigger peak performance. Well, for the edge device, the most popular is W4 A16. Okay? So in the low batch area, it wins over this yellow curve, because the weight dominates, memory bandwidth dominates, is the bottleneck. But once it peaks, the peak performance is the same as P16, and it's 2x smaller than the W8 A8 version. Okay, so the red is the baseline. We have these two solutions. Basically, SmoothQuant is this yellow part. AWQ is this green part. Our question is, can we combine the best of both worlds to have something into this W4A8 part, okay, into this green part? So that's the motivation and that's the goal for the QServe, is to combine the best of both worlds in both the small batch and also the large batch setting, using the 4-bit weight, 8-bit activation, and 8-bit arithmetic. There is some prior exploration, but unfortunately it failed to achieve very good throughput. So this is the baseline of TensorRT from NVIDIA, and this is Atom, this is Parrot, W4A4. They're all W4A4. But unfortunately, the throughput measured by tokens per second, it's even smaller. It's even half compared with TensorRT's W8A8. So they reduced the precision, but unfortunately, without a good engine, no speed up, but 2x slowed down. And also that brings significant accuracy loss using the W4A8, W4A4 manner compared with the higher precision version. So we try to dive deeper to understand the overhead in quantized jam on the GPUs. So CUDA core operations in the main loop is pretty expensive. We try to do as much processing in the tensor core, not the CUDA core, and to try to do as little as possible such things such as the scaling in the tensor core, in the CUDA core, inside the main loop. Okay, this is the main loop. This is the epilogue. Okay, so this is a TensorRT LLM, NVIDIA, the framework from NVIDIA, the int8 weights and int8 activation. So the main loop is all processed. So orange means the int8, the red means IP16. Only in the epilogue we do the scaling on the CUDA core. So this is actually pretty efficient. And let's take a look at other alternatives, why some work is not efficient. For example, Atom, they do tensor core, the int8 into 4 operations. This is in green, into 4. But they have to do a lot of CUDA core operations in FP16 in the main loop. Okay, so this is the main loop. And particularly it's doing the scaling of the partial sum. Okay, the partial sum, we have to multiply them with the floating point 16, FP16 scaling factors right here. So partial sum in jam will consume much more registers compared with the input. Okay, and the partial sum dequantization, okay, from int 32 to IP16, dequantization require much more computation. Okay, that's why it's even slower. And compared with, this is the TensorRT LLM's implementation of AWQ. Okay, 4-bit weight, 16-bit activation. This is the 4-bit weight in green. In the CUDA core, it converted into 16-bit floating point. Very quickly converted into 16-bit floating point. And then all the major computation is done using the 16-bit floating point. So this conversion is the input conversion. Okay, it's much more efficient compared with the partial sum dequantization, which require much more register than input, which have much smaller pressure using the registers. So what we propose here is using the 4-bit for the weight, 8-bit for the activation, and 8-bit for the arithmetic. So first convert this 4-bit weight into 8-bit integer, okay, and do all the matrix multiplication in 8-bit integer right here. Do the summation. So this is the main loop, and outside in the CUDA core we multiplied with the scaling factor as the epilogue. Since this is outside the main loop, the processing is much more efficient. So the take home here is that you try to do this dequantization not in the main loop, but in the epilogue, and also try to minimize the conversion, the dequantization of the partial sums, which consume much more registers. So quantizing the KV cache to 4-bit is actually quite challenging. So we are observing there is actually a lot of outliers in the keys. So this is the value. Value is pretty smooth, but the keys, the supposed rope. We talked about rope previously. The supposed rope keys, some channels has pretty big outliers. So we can actually apply smooth attention to using a similar approach as SmoothQuant to smooth away those outliers in the keys. So since the keys will be multiplied with the queries, we want to push the quantization difficulty between the query queue and the key. Okay, we are going to use the scaling factor will be just related to the k, since we are pushing all the quantization difficulty from k to the q. Since query is pretty small, we can keep them in IP16 and keep all the push all the quantization difficulty from P to query. That's why here we have only a single term, which is K, there's no Q. Another technique to dequantize from 4-bit unsigned integer, unsigned int 4 to signed int 8 is the sequence between the subtraction and the multiply. Okay? Remember, we have a bias, we have a 0 point. We have to subtract it and then multiply it by the scaling factor. Unfortunately, using this way, it will lead to overflow. So this is original quantized weight, binary representation, a hex representation of the quantized weight. If we first subtract the 0 point, we get this value, a minus 1 minus 8. This is the hex representation, same as before. Here is the decimal representation, here is the hex representation. And then we multiply with the scaling factor 2. Unfortunately, the carry bit will lead to overflow. Okay, originally this is 14, minus 10, it will be E2. So the carry will overflow the next value. So this actually can be solved by multiplying first. We first multiply with 2 and then subtract by minus 16. And this will lead to no overflow. So the sequence matters. Previously, if you want to calculate something like, you want to scale it and then subtract versus subtract and then scale, that did make a difference at low precision. So QServe actually outperformed the state-of-the-art inference libraries, such as the RTN, AWQ, and the Conrod, Atom, and QServe. actually have a pretty low perplexity under W4A8 KB4 quantization. And this is the speed up, the throughput, measured on A100 on the first row and L40S on the second row. Okay, so let's now switch gear from quantization to pruning and sparsity. So I'm going to talk about weight sparsity, contextual sparsity, and also attention sparsity. So this work basically prune the weights. Naively, previously when we are pruning the weight, we look at the weight. If the weight is small, like these weights are small in blue, then we are going to zero them out. And this paper basically is showing that we should not look at the weight. We should look at the activation. So this is the activation that's going to be multiplied with the weight. The multiplied result will be here. For example, 1 is multiplied with 8 and becomes 8. And then we look at the values that's pretty small. Okay, so this 0 is small, 4 is small, 3 is small. We look at the result of W times the input activation. Okay, and we profile and eliminate those small output activations. Okay, using such activation to guide the weight pruning. The intuition is very similar to AWQ, where we should be activation aware. Look at the weight, look at the activation when we are either pruning the weight or quantizing the weight. So this is showing the comparing the performance of the magnitude-based pruning, Sparsity and Lambda. And this method is showing that the weight times the activation as the criteria for pruning actually outperforms the magnitude-based pruning. Okay, contextual sparsity. So people find when we are pruning the activations, the static sparsity hurts. It should be input dependent, right? So contextual sparsity is basically saying that a small input dependent sets of redundant heads and features exist in the large language models. So we can use a predictor, train a predictor to predict which attention head is useless and which dimension of the MLP layer is useless. And we train such a predictor using the previous layer to predict for the next layer which dimension is useless. We can safely remove those tokens. Okay, so this is showing using static sparsity, the accuracy quickly drops when the parameter reduces. And this is showing using contextual sparsity, the accuracy can be well maintained at a very high parameter reduction ratio. And on the right-hand side is showing the speed up, okay, compared with the baselines, DJAWU, which is showing this contextual sparsity can bring very reasonable speed up compared with the baseline. There's also the mixture of expert as a coarse-grained sparsity, which is showing that given different input, different tokens generation will use different part of the weights. Okay, for example, when we are generating this token, the router routed to the second FFN versus another token will be routed to the first FFN, which is showing we can use different part of a model to generate the next token. Okay. So this is showing the router. Okay, so we have several experts. Here we have 3 experts. Altogether we have 6 tokens. Here is showing if the first expert is responsible for these 2 tokens. The second expert is responsible for these 2 tokens. We can design this capacity factor to be tokens per batch divided by the number of experts and times this capacity factor. If the capacity factor equal to 1, it's showing that altogether we have 6 tokens. So tokens per batch is 6. Number of experts, we have 1, 2, 3. We have 3 experts times 1. So every expert can process at most 2 tokens. And if the capacity factor is 1.5, every expert can process at most 3 tokens. Okay, at most 3 tokens. So there's empty select token for expert 2 and 3. So the routing mechanism can have different approaches. One is by token, the other is by expert. So here it's showing token 1 can choose between expert 1, expert 2, all the way to expert 5. And token 2 can also select its preferred expert. The other way is per expert. So expert 1 can choose the top K to handle token 1, token 2, or token 3. Expert 2 can also choose to handle different tokens. We can also do this global assignment, expert assignment. Which token gets assigned to which expert. So there's also the attention sparsity. Okay, so Spartan is showing that we can do token pruning and head pruning. For example, given a sentence as a visual treat, the film is almost perfect. It has 11 tokens and 12 heads. We can prune it to only 5 tokens and 10 heads as treat, film perfect. And then prune it to only 2 tokens, film perfect. It can still classify the sentiment to be positive, which is showing the natural language has a lot of redundancy and it's safe to remove lots of the redundancy and still achieve the similar goal. On the right-hand side is showing the attention mask to show how do we perform this token pruning. So we look at the attention map. I bet the video game is a lot more fun than the film. And this is the attention map. For each token, we sum the attention score across the entire column. For example, will be summed up to 0.4, very little attention across different tokens for this token. Versus fun, the cumulative attention score is 1.9, it's pretty high. Like some of the tokens attend very heavily to this token, so it cannot be removed. Tokens like I, the, and period, they receive very little attention, so we can safely remove those tokens. So in summary, tokens with small cumulative important score will be pruned. So following this work, this H2O, this paper finds it's possible to prune tokens in the KV cache, which is very similar to the Spartan work. Okay, so it also look at the attention map. Now the difference is now it's causal. Okay, so just look at the cumulative attention score. If a certain token has very small cumulative attention score, it's going to prune it away. Okay, so next chapter, let's talk about LLM serving systems. Let's first introduce the metrics for LLM serving. So the first concept is about time to first token. Okay, it measures after you type your question, your query, how quickly does the large language model begin to respond to you. Okay. So this is very crucial for real-time interaction. You want to input your question and you want to immediately get an answer. And there's also a concept called time per output token, okay? Tokens per second, which is the time that is taken to generate each output token. For example, you can generate 100 milliseconds per, it takes 100 milliseconds to generate each token, then that corresponds to 10 tokens per second. And that is roughly the threshold. Above that, it will feel it's very interactive, but below that, it will feel the large language model is pretty dumb. It can generate very, very slowly. And the total latency will equal to the time to the first token plus the time per output token times the number of tokens to be generated. That's the total latency to complete the task. And the throughput is the number of tokens generated per second across all the requests by the inference server. So the goal of the inference system optimization is to minimize the time to the first token. Okay? And we want to maximize the throughput and also reduce the time per output token. And there's usually a trade-off between the throughput versus the time per output token. We are going to see that. And there are several heuristics for model evaluation. For example, the output length. Since the output generation will dominate the latency, the input length that will impact the time to first token. And also the model size, usually the larger the model size, the slower the inference. But it's not proportional because, for example, the 7 billion parameter model is about 2x. The latency of a 13 billion parameter model is not proportional. So the first optimization technique is called VLM, called paged attention. Okay. So previously we talked about the KV cache. When you have a lot of tokens, the KV cache can grow pretty large. This is the equation how to calculate the KV cache we learned previously. And there are several wasting. There are several scenarios of potential waste in the KV cache system. So the first potential waste is the internal fragmentation. We have to over-allocate several spaces for the KV cache due to the unknown sequence length. Okay? So for example here, we have more than 2,000 slots that is never used. We may also have this reservation fragmentation. Okay? So it's not used in current step, but it will be used in the future. For example, artificial intelligence is the future of technology. The request is currently here, we generated 2 tokens, but we have 3 tokens that has not been generated. We still have to allocate space for them, but it's currently not being used. We still have to allocate the space for them, that is called reservation. Also, there's external fragmentation. So this is just one single request. When we have multiple requests, they may have different sequence lengths. To deal with such fragmentation issue, if you have taken 6.191, you'll remember the operating system has this paging mechanism where different processes they can share a page table, they can share the memory space using page tables. Similarly, we can also use the similar memory management system for the large language model, just to use the virtual memory and the paging. So we can have the KV page to manage that. For example, in this case, the prompt is Alan Turing is a computer scientist. So initially, let me play this relatively slowly. Initially, we are going to fill the KV cache by having allocated 2 blocks. Each block has 4 entries. And then as we run out, we allocate a new block and update the block table to show which is the physical page number. Okay, so physical page number 7 for Alan Turing is and it has 4 entries. First block is computer scientist and mathematician. Okay, so we are keeping the physical block number and also the number of filled slots. In this way, when we are having 2 requests, request A and request B, they can work with the same physical KV block. Okay, the yellow part belongs to request A, the green part belongs to request B, and they can interleave without worrying about the fragmentation issue. And the good thing about this VLM is that we can share. Okay, we can share the prompt. So during the parallel sampling, say this is the prompt. Future of cloud computing is bright and poised for further growth, intertwined with advancement of artificial intelligence, likely to be characterized by several key trends. So for different outputs, they share the same input, and then you can allocate the same, just a single KV block for this shared prompt. So they both have them, both sequence A and sequence B has this prompt. Rather than allocating duplicated KV blocks, we can just modify the pointer that both of them point to the same physical KV block. And then they can have their own KV block for the parallel decoding. Flash attention, a very important concept. So when we are generating the attention matrix, it's n by n, that's pretty big, it's O n squared. Okay? So the key idea is to use tidying to prevent you have to store all the n by n attention matrix in memory. So we have learned about the tidying idea in our parallel processing class. That's exactly the same motivation. We want to calculate the attention results of Q and K and immediately multiply that with V without having to materialize that. This is comparing the PyTorch implementation, this is comparing the flash attention implementation. The fuse the kernel fusing this QK transpose and then times V, these two kernels into one, actually can dramatically save the latency. And this is comparing the baseline PyTorch in blue versus flash attention in yellow versus flash attention 2 in purple. Very significant speed up for with and without the causal mask. The left is without causal mask, the right is with causal mask. The next technique is speculative decoding. Okay? So the generation of the token is memory bounded. Okay? No matter how many you generate, if the batch size is pretty small, you are bottlenecked by the memory bandwidth. So the idea is to use two models for speculative decoding. One is a small model for generation, also called a draft model. The other is a large model for verification. Okay? We can, running this large model is pretty expensive. So we only run this small model auto-regressively, and then generate many tokens in serial, and then verify them in parallel. Okay? So the small model generates K tokens auto-regressively, and then the K generated tokens will be verified in parallel. We feed K generated tokens to the large model, the 175 billion model, to run them in a batched manner. So running K token will be roughly similar to running one token if K is not too large on the GPU due to the parallelism. So let's see example. So this is using two models, a small model and a large model. We use the small model to generate draft tokens, 4 draft tokens generated one by one auto-regressively, and we feed these 4 tokens together into this large model in the batched manner. It's non-auto-regressive, it's parallel, and then verify if the generation is correct or not. If it's not correct, we can redo it, do it again by the small model. So here is an example. We are generating these green tokens by the small model, and then use the large model to verify them all together in the batched manner. And we find, this last token is incorrect, then we have to call the small model to generate again. And then verify it, find something is incorrect, generate again. So the green part is accepted by the accepted token. The red part is the rejected token, and the blue part is the corrected token. Finally, it can achieve about 2 to 3x speed up with identical output. Okay, so the last technique is batching. Okay, so why do we need batching? Running multiple inputs simultaneously in parallel can maximize the throughput by fully utilizing the GPU resources and avoid idle time. There are several batching methods. Of course, the simplest way is no batching. Okay, when a request arrives, then we just immediately process that. We may underutilize the GPU resource. Static batching, which is wait for full batch of requests before we can process them. This is pretty good for offline tasks, like scheduled tasks. You have like 10,000 images to label, take overnight, and then you can use static batching. But it will increase the latency for real-time tasks. You may have to wait for the batch to be full for you to process them. There's also the dynamic batching. Okay, so the batches are processed either when the batch is full or a predefined time has arrived. And last part is the continuous batching, also called in-flight batching. Okay, have a finer granularity, token by token. And let's see example of dynamic batching. So static batching, basically you have to wait for 4 requests to arrive, which may take a long time here, take a long time here. Dynamic batching is saying either when the batch is full or when a preset time has arrived, here this amount of time has arrived, then you should process them, even if the batch is not full. This is like a bus will leave when it's full or when the timer expires to ensure minimum wait time. This is good for the generation has uniform inference latency. Like image generation, you have a predefined, you have the known fixed model inference latency. What if the generation is not fixed? You can generate different number of tokens for different users. So this is the in-flight batching or continuous batching, okay? So compared with this kind of dynamic batching, we don't have to wait for this extra slack, but we can immediately push the second request when the first one has finished, okay, in a token granularity. This is like when a bus where passengers can get off the bus at different stops, we can immediately make space for new riders. Okay? So here we have people get off the bus, and then we can immediately make this space for new riders. This is continuous batching versus dynamic batching. All right, we pretty much covered all the techniques now supported by TensorRT LLM, a large language model inference library by NVIDIA. We talk about multi-head attention, multi-query attention, group query attention in the last lecture, in-flight batching, page KV cache, int8, int4, weight quantization, SmoothQuant, GBDQ, AWQ, T8, and rope. So we are going to cover tensor parallelism, pipeline parallelism in the future lecture. A lot of content today. Hope you master them all and enjoy lab 5 and lab 4. Thank you.